So welcome back for this second session of today. So it's again a great pleasure to introduce the speaker to you. So Mehrdad Asad. Mehrdad is a postdoc in our lab. And he has been working on explainability, so he will, of course, tell about this topic himself. But what else can I say? The Mehrdad is doing a great job on the EU project PEER. So he's very active in managing 4 use cases. So the idea of the project is it's on sequential decision making. That's the specific setting, but it's also about how can we make AI algorithms in this sequential decision making setting that really fulfill the needs of people. So we want to co-create them with the users before they are actually made. So you can imagine that this is a challenging job to talk to 4 different fields with different needs and to manage this all and unify it in a single approach. But Mehrdad is doing this very well.
Thank you.
So yeah, I'm now looking forward to know more about, I guess, also your previous work. So the floor is yours.
Thank you very much for the kind introduction. So hello everyone and welcome back. Today I'm very glad to actually be present as a BrIAS fellow, and I hope you enjoy the talk. I will be mainly talking about how we actually need to also consider explainability as a component in the machine learning pipeline or also the software development. So just to give a brief outline, I will be presenting about the classical software architecture and how usually the software architect should actually have different concerns when designing an architecture of the software. But especially nowadays, we are facing on machine learning and AI component as a part of these subsystems. And we need to also consider concerns related to XAI during the design. And we will be studying some of the techniques that are state-of-the-art for explainability. And the work that we have done so far, we will look at a unified platform. We call it a spatial platform where we actually integrate all of the XAI and also different metrics for evaluating AI. And then we will look at some use cases and ongoing works that Anders mentioned. So in the classical software architecture, just to give a context to this talk, I would like to illustrate how classical software architecture is actually evolving. So if you remember from the past decades, so we usually had some software systems that components are interacting with each other. And the software architecture mainly was actually responsible for technology choice, database choice, and UI UX design. But as this software architecture is evolving, we have new components like machine learning models and also the AI algorithms that fit data from these software subsystems and also take some optimization and decisions on behalf. But then new concerns like data quality and also model accuracy and privacy arises as part of the software architecture concerns. So as the architecture evolves, we have different stakeholders also involved in the project. But nowadays, as long as we are facing the challenges with opaque AI and also the transparency that is required for the AI and decision making, we have different stakeholders that I will be actually talking about in the few slides. So as you can see, even these machine learning models recently, for instance, federated learning, we have distributed clients that add more complexity to this architecture. And it's very important to study how data quality and diversity and distribution of data would affect the outcome of these systems, and how we can evaluate the resilience of the models that are generated. So most of the talks until now in the BrIAS seminars actually already shown this significant advances in the statistical machine learning in compared to the symbolic approach that we had so far in the past, which was actually rule-based and much more understandable by the users and also data scientists. But now as the deep learning and also deep neural networks actually make this advancement much more understandable or envisioned for the data scientists, it is very important to consider to study this complex relationship that usually these deep neural networks come up with. And that's why there is a need for XAI. So for instance, considering this highlights, for instance, how opaque decision making is now complex that requires more human in the loop understanding, and also how this black box AI actually affect the trust of the human users who are actually interacting with this decision making. So that's why this is very important to consider approaches like explainable AI to try to make the decision making more transparent for the users and try to show this relationship among the data that the models are trained on. And one of the important regulations, which is called General Data Protection Regulation, actually in 2016 highlights that the users has right to be provided with enough explanations and also meaningful information when they are actually facing such AI system. And that's why explanations or explainability is part of the systems nowadays, and that requires some efforts to make these explanations more meaningful for the users. And the user could be even a data scientist who is developing the method or developing the model, but also users or customers of some AI decision-making system. I will be trying to actually give a summary of recent works on XAI and how, for instance, the performance and explanations make a trade-off today. So, for instance, we have deep learning methods achieving very high performance actually results, but on the other hand, because of the complex relationship that they find usually in the data set, they are not explainable enough, or they have some complexity that is not understandable by the users. But on the other hand, we have different simple approaches like linear regression methods that it's understandable because of the weights or also the proportional importance of the features that is easily understood by the users. So there is a trade-off that we need to think about when developing some AI methods based on the use case, based on the criticality of the use case. We can approach different models to also not only cover performance, but also consider the explainability and how explainable they are. XAI actually covers 4 different perspectives. I will be actually talking more about the 2 in the down, in the below of the actually, for instance, explain to improve. It actually allows identification of flaws during the development of the AI, or also explain to discover, for instance, how different relationships are found within the data. But also, it is actually used to explain and to build trust with the users, which is out of the scope of this study, but it is something that I will be presenting in the future if there is some opportunity. But for instance, we need to consider human readable justification for a decision to make the human to trust in the decision. And usually this is done by studying with the users, having questionnaires and asking users how they actually trust the system, and the decision that is made. And also the right to explanations, which is about how the user would be able to change a certain decision, which we call it counterfactual. Because counterfactual is one of the explanations that is very user-friendly, because the user would be able to change a certain decision of the AI or the system, and it is very valuable. But as I said, the main talk will be targeting the two. Information extraction and identification of the system flows. So this slide, actually, I want to emphasize different approach and different techniques for explainability. For instance, on the left, you see directly explainable models, which I just mentioned. For instance, the linear models, which are simple enough, or decision trees. But just to highlight that, for instance, decision trees are explainable on certain depths, because, for instance, there were many studies that as you actually have a complex relationship within the decision tree, it's not explainable at all. But those are models that we consider as directly explainable. And there are many post-hoc explainability methods, considering global explanations for the model, which actually try to globally explain certain models and the relation that is found. And also some of the methods consider explaining a certain decision or one instance, which is, we call it as a local decision making or local explanation. And then the other approach are actually counterfactuals, trying to generate new instances based on some hypothesis that the user might have, trying to show a user how he or she might be able to change a decision of the system. For global explanations, usually the methods or the approach that the researchers has actually used so far are feature importance, showing what features play a critical role in certain decisions or the outcome. And also knowledge distillation, that, for instance, you have a deep neural network, you try to distill knowledge from that deep neural network, and then use a simpler model like decision trees to approximate the complex model. But still consider the trade-offs, and then the lack of performance in compared to the general or in compared to main complex model. And then also there are explanations for the local decisions, then same as the one that I just tried to mention, they also consider local feature contributions towards some certain outcomes. But usually when you talk to AI people, they have concerns like that, what the explanation looks like. So depending on the data set that you are working on, or the use case, for instance, the explanations would be different. For instance, in the case of tabular data, usually the explanations show some values that shows the importance of the features of each record. Or in the case of images, they usually highlight the pixels that resulted in certain decisions. And also the text, this slide actually mainly is classification task. So that's why you can see the different classes that is classified. And then we show certain features that were important for this decision. But then just before the session, I tried to generate a nice prompt for to showcase how AI or explanations would be appear in the case of generative AI and ChatGPT. I just ask a question like, I'm a postdoc researcher, how to actually continue my career, and then there are some actually approach to take. But then when I asked the question, why did you give me this answer? For instance, the generative AI tried to give me some important feature in my question, highlighting why the question was based on. So it's not only the classification task, but also the sequential decisions, also the time series data that would be enabled to generate such explanations. But another question in XAI is, how should we evaluate it? There are two different approaches. One is actually based on the user and the user studies. Usually we try to see how explanations are understandable by the user to solve some specific task or the performance that he show on the specific task. And also the satisfaction of the user, how the user is satisfied with the explanations. Can he actually make the decision on behalf of the AI overcoming the task? And also predicting the AI decision based on the explanations that we show. Or also the inherent metrics that we actually computationally evaluate, like fidelity, which actually measures how accurately the explanations reflects the true decision-making process. So it's very important that I will show in the next slide, for instance, in the case of LIME approach, how the explanations reflect the true process in the back end of the AI. And also stability, which evaluates how consistent the explanations are when given similar instances. So we need to actually consider the stability as a metric when generating the explanations, because similar instances should have similar feature importance and be same. And there are some other metrics that I would like to skip here, but there are references that you can actually look for it. But for the first method that I would like to introduce is actually local interpretable model agnostic methods, which is called LIME. LIME actually is a local fidelity method. In the locality of the instance, they try to approximate it as much as it can. So it's very similar to the original model output. And then it is simple and linear. So consider we have a deep neural network on the left. And actually, LIME consider this as an optimization problem, where actually on the instance that is need to be explained, they try to approximate it using a linear regression, which actually tries to minimize the loss between the linear model that is actually generated and the real model, which is actually F. And also a regularization term, which tries to keep the model as simple as it is. So it's kind of locally approximating the complex model. That's why it's called local interpretable model. But just to highlight, one of the actually drawbacks of such approach is that it cannot recover complex relationships. It's just simple linear. So that's why some of the relationships which are complex and the feature interactions are not considered. And that's why now we have a new method called SHOP. It's based on a cooperative game theory approach, theoretically justified, and then it is able to generate both local explanations for a specific instance and also global explanations to actually have an overview over the complex model and how the features are important, and also it could be used for handling a complex relationship and also feature interactions. So actually, SHOP treat each feature as a player in a cooperative game, and then they try to model this prediction as a, for instance, a payoff could be considered as the prediction of the model for certain instance, and they try to distribute the payoff or the prediction score to different features. So kind of fairly distributing the features among distributing the score among the features. So here, for instance, F is the set of all features, and then we have the subset of features excluding I, which is S, and then for instance the function fs is the model prediction using only the feature S and also in combination with the I. So trying to actually consider every combination of the features. That's why SHOP is one of the complex methods, requires much more computation than LIME, but it's still having nice results in case of fair distribution of a score among the features. SHOP uses different plots for conveying this information. For instance, force plot, waterfall plot, and also Bayes-Warm plot. This is actually an example of the Bayes-Warm plot for showing the feature importance, the global feature importance of the model using SHOP values. Actually, this is an example for loan agreement prediction, I guess. And then it shows how different features play a role in some certain prediction or the decision of the model. And then we have layer-wise relevance propagation, or we call it LRP. Actually, this is a top to bottom approach. What I mean is that, for instance, in the case of two previous approaches, like SHOP and LIME, usually we try to compute the feature importance for a specific features at the runtime. But here, once we make a decision, we propagate back the weights, for instance, in the case of neural networks, to the features which were actually, or the neurons that were important. And then that's why it's called top to bottom approach. And then also is mainly designed for interpreting neural networks and follows a conversation principle, meaning that the total relevance of the output is propagated fairly to the features layer by layer. That's why actually propagating the importance back to the feature set or pixels. For instance, in the case of images, we can see that the classification task, they try to highlight the features which were mostly important for certain predictions. And actually, the equation also compute the relevance of each layer or neuron to be considered as important in the case of LRP method. And one highlight is that it directly requires access to the model structures. So this is not model agnostic. So for instance, in the case of LIME SHOP, you can apply that to any model, but here the model is specific and you should consider having access to the model structure. And then counterfactual explanations. So usually counterfactual explanations describe a causal situation. For example, I have an example here, but okay. If I hadn't taken a sip of this hot coffee, I wouldn't have burned my tongue, for instance. The kind of explanation, causal relationship, and then a counterfactual could be I didn't drink the coffee at all. So that's kind of another hypothesis that a user might be interested in to know what could be changed to result in different outcome. But it's important, in the case of counterfactuals, there are some metrics and criteria that we need to consider. For example, a counterfactual instance produces the predefined predictions as closely as possible. So usually a user defined a certain interested outcome for the AI decision, and then we try to generate counterfactual based on that predefined outcome. And it's very important to actually generate an instance that could be closely to the predefined prediction. And a counterfactual should be similar as possible to the instance. We cannot change a lot the features to generate the counterfactuals. I mean, it's kind of optimization problem that we need to consider changing few amount of features and also by some certain minimum value, not to change much. So kind of against the counterfactual explanations. And also it should be possible in the real world that counterfactual instance should have some values, some certain values that are logic, and following some principles in the real world. For instance, one of the methods that was actually proposed by actually Wachter, the first term is actually considering the differences between the predefined prediction and also the model prediction of the new instance, which we call it counterfactual, and then the second term is actually a distance measure, how similar those instances are. Kind of, we need to optimize it based on the difference between the values of the features, and then we try to optimize this loss to generate the counterfactual for the user. And one of the drawbacks of this approach is that actually they just consider the two first criteria, which was the distance of the counterfactual, and also the other one, which was the distance between the two examples that we need to consider. And they do not consider, for instance, unrealistic feature contributions or feature differences. And then to overcome that problem, in 2020, a multi-objective optimization problem based on these criteria was actually formulated to consider all of the four criteria that I just mentioned in the few slides before. So they actually try to use the multi-objective optimization approach and also genetic algorithm to generate such a counterfactual. And to the best of our knowledge, at the time that we were developing a uniform, trustworthy platform that a user could actually upload their model or also use the platform to apply machine learning models, the different actually explainability approaches were somehow isolated and they were not integrated in single platform. So what we have done so far, we tried to generate or create a novel component, which actually we call it trustworthy augmentation, that not only consider some XAI methods to be applicable for some use cases, but also there are different metrics such as fairness and trustworthiness and resilience that could be implemented in the platform, so a user could easily access this through some APIs and generate explanations to increase its trustworthiness. Both a user could be a customer accessing some model, or also a user who is data scientist trying to generate a model. So this is a kind of our recent works on the defining a novel architecture and also implementation of this. So for instance, we use the microservice architecture approach, where we actually have defined different XAI methods as kind of microservice and totally independent of each other. And also different metrics such as fairness that are integrated in a single platform and could be accessed by just some API gateway. For instance, in the case of us, we just implemented that using Kong, which is one of the well-known and lightweight API gateways to let the users access all of the services at once. So some of the use cases and results in the case of adversarial machine learning. So we used this implementation to apply that for different use cases. For instance, in the case of medical electronic calling application, actually it's a kind of mobile application that uses accelerated data of the smartphones to detect the falling of the elderly people. And we use the dataset such as Unimap Sharp dataset, actually representing different activities that a user might have in a home. And some of them, for instance, 8 classes, if I'm recalling correctly are considered as a fouling activity. And we try to use actually adversarial attacks to evaluate how XAI could be helpful for evaluating this type of attacks and understanding the behavior of the model in case of attack severity. So the two well-known attacks we have performed for this adversarial machine learning was actually black box attacker for this scenario, where the user do not have any knowledge of the model or the logic, but just the training data. So they can actually try to, what we call it as a poisoning attack. They can try to lower the quality of the data just using perturbation attack or just changing the features, values, or also label flipping attack could be actually changing an instance labels to something that is not correct in the real world. So this type of attack was performed to see how, for instance, in the case of shop value, could be useful enough for detecting the severity of the attack and poisoning attack. So therefore, actually, we have tried different AI or machine learning approaches to see which one actually could be best as a baseline. So as you can see, for instance, a deep neural network is the one that we that performed the best on our data set. And as we increase the level of poisoning attack randomly by some percentage, we can obviously see how model resulted in a bad performance in the case of test. But then the novelty of this approach is actually how we can quantify these poisoning attacks using Shapley values that I just described in the slides. So basically, as we have considered a metric called average Shapley distance. At the test phase, we try to see how model actually globally is explained by the Shapley values. And then once we do some poisoning attack, these Shapley values shows a significant change in the feature importance, which we can call it as a quantification for detecting the attacks. But also, one of the open question is actually we have different type of attacks. We still need to understand how these methods are useful for detecting a specific type of attack and not just the severity of the attacks. And then another use case is actually network activity classification. So this is actually a work that we have done with some colleagues. The data was provided by a company called WithSecure. They actually internet service provider trying to understand the user behavior. So here the goal is actually to identify a type of activity that is user has actually during browsing the internet, whether is it just streaming or is actually some other activity. So basically the data set was a real data set that we have received from our colleagues, and then we have different adversarial model here. The difference is actually the model is accessible by the attacker. So for instance, it's very common in the people where actually there is some intruders inside the organizations actually having complete knowledge of the model, and they can perform such attack. And also we have different attacks such as evasion attack, actually called fast gradient sign method. This is one of the attacks that we performed so far. We try to actually add noise to the data based on the gradients of the model. And also the two label flipping and label swapping attacks that we just considered in the previous use case. So kind of targeted attacks. Again, the same results that shows how Shapley value could be considered as a detection mechanism. So for instance, in the figure on top left, you can see that the classification task actually considers how features are important for this type of model without poisoning or benign data when the model is trained on the benign data. And then once we try to do the evasion attack on the data, we can see that the order of the features, which were important for the benign model, completely changed. And then it shows the applicability of the SHOP values for detecting the attacks of evasion. And then the two-figure below actually shows, we tried to introduce two novel metrics such as impact and complexity. Actually, impact is how the model was how the model misclassified the Poisson data, and then the complexity is actually how complex was generating the instances for the to confuse the model. So basically showing the effect of a Poisson attack on these two metrics. As the Poisson attack increases, the complexity and also impact increases linearly. And just to highlight also some of the works that we have done so far, because the theme of the BrIAS was also sustainability. So it's also important to consider computational overhead and explainability and scalability for the metrics that we have developed so far. So we also performed some simple experiment to see how many concurrent users can access to the services that we have developed, and actually how the scalability looks like. For instance, in the case of the left, so we can see that once we increase the number of users accessing the metrics concurrently, the response time is actually not very increasing suddenly, so it's actually stable enough. But then the other two methods like SHOP and LIME, which are actually well-known methods for XAI, for both tabular data and also the images, we can see that at a certain amount of time, the computation time increases to up to 8 minutes for single image. But then still, it's some thing that we are now doing much more experiments to see what happens if a certain instance is asked for different services to be explained at the same time. So to have more insight about single instances. And then what we are now working on to actually apply the same methods for reinforcement learning setup. So actually in the reinforcement learning setup, we have some environments and the agents taking some actions and trying to optimize some policy based on some reward function or goal. So what my colleague has done, for instance, in the case of the first simplifying the agents model, trying to, for instance, distill a knowledge from the deep neural network, that is deep reinforcement learning network, but then trying to create a data set and then generate a simpler model like random forest or the decision trees. But the problem is actually the agent is not able to explain a single instance. It's just globally explaining how the agent behaves. But then different approach for explainability is, in the case of reinforcement learning, is actually how we can communicate the preferences and the rewards of the agents to the human based on the user preferences. But the thing that I'm working on it now is actually how should we explain an agent decisions based on long-term consequences, which actually would be interesting because it would be influenced by both the dynamics of the environment and also the actions that the agent takes. So it's very important to understand how we actually can generate explanations that could be answer some questions. For instance, what is likely to happen from the state, some specific state with the current policy. So showing the user a long-term behavior of the agents and the outcome of the policy. So now, yeah, that's what we have done so far and what we are now working in currently. So thanks for this opportunity, and if there is any question, I'm happy to hear that.
Questions?
Thank you for the presentation. I have a small question. So in one of the slides, we had like 4 plots. A bit before, there was, and you were showing the poisoning increasing.
This one?
No, before again. I'm sorry. Yeah, this one.
Yeah.
How comes on the bottom left, like the yellow line increases with the poisoning? How can that be? What is?
Because once you actually, that's a good question, because at some point we have observed that when you actually increase the poisoning level up to certain amount, like more than half of the data set, then the distribution of the data completely changed. Then that's why sometimes the performance also changed based on the training set that we have actually imported new data that is fake. That's why.
Okay, thanks.
Hi, thanks. Sorry, it's great to see some attention to explainable AI in this seminar series. So in my field, there's a lot of interest and also a little bit of gloom under the heading the disagreement problem in explainable AI. And so the finding there is that basically with many of those explainers that you also, many of which you explained to us today, have very nice theoretical motivations, but maybe those theoretical motivations of assumptions are sometimes violated, and in practice they produce extremely different explanations. So if you apply SHAP, integrated gradients, and all the other ones you mentioned, if you apply them, especially in the LLM world, for instance, you get radically different explanations. Have you run into that disagreement problem yourself, and you have ideas of how to move forward there?
I think that's a nice point, but one of the highlights that I made in the beginning, most of these methods were evaluated computationally, and we really need to design a questionnaire that we can do a user study with the users to see which one actually would be meaningful enough for the users. That's something is actually out of the scope of these presentations, but what we are now doing within the project, we actually develop different XAI methods, but before doing that computational work, we try to simulate the behavior of the explanations and to study with the users. So that's something that I would say I agree, but it's still open question within the community.
I also have a question about the reinforcement learning slide you had at the end.
So, sorry, can you repeat?
The reinforcement learning slide that you had at the end.
Yeah.
What do you think would be a good approach for explainable RL? You discussed a few different ones, like either explaining a local decision or the whole model. What do you think is a good approach for explainable RL?
I would say that one of the actually methods that would be much more reasonable for RL setup, because we have an agent taking sequential decision making, is actually contrastive explanations or counterfactuals. Because, and also one of the points is that you should consider generating the counterfactuals that explains how early changing the decision would result in different outcome, because some of counterfactuals try to generate different different policy, but actually it's not the case that would be understandable for the user. I would consider generating counterfactual based on the specific state that you have, showing how the change into the state would result in different actions, step by step wise.
So that would be the agent building its own model of the environment and estimating the next states depending on the action or something
Yeah.
like this?
Yeah, something like that. Yeah.
Thank you.
And also trying to align with the mental model of the human and the users, because sometimes the difference between the mental models actually result in misunderstanding between the communication between the user and AI. And first we need to see if the models of the agents aligns with the mental model of the user, and then that requires also some effort, and then trying to explain based on this alignment.
Thank you.
Yeah.
Okay, no more questions. Then let's thank our speaker again.